Hi, welcome back to my YouTube channel, Chi Analysis. In this video, we're going to solve for the shear force and bending moments and also draw diagrams for the shear force and bending moments of this beam. This is an overhanging beam. As you can see, there is no support at C. It's a free end. So we are going to solve for this beam right away. The first thing to start with is a support reaction. We have 4 points to consider: RA, RB, 2 kilonewton per meter, which is a UDL, and 2 kilonewton, which is a point load. We have to first convert the UDL to a point load, which is using the force to multiply the distance 6. Resolving this, we have our equation 1 as RA plus RB is equal to 14 kilonewton. So we're going to take moments about A in order to derive RB. We would not consider A because we're taking moment about A, so we're left with 3 forces to consider. The first is the UDL, which is 2 multiplied by its distance multiplied by the distance divided by 2, because it's going to be converted to a point load that will be acting at the center of its distance. This is a clockwise moment. The next force is an RB force, which is an anti-clockwise moment, multiplied by its distance, 4 meters. Next is a 2 kilonewton force, which is also a clockwise moment, multiplied by its distance, 6 meters. Resolving this equation, we have RB times 4 is equal to 2 times 6 times 3 plus 2 times 6. So we have our RB as 12 kilonewton. The next step is to substitute the value of RB into equation 1 so we can determine our value for RA. The value of our RA is 2 kilonewton. I'm just going to write down the values here so we do not forget. Now the next step is to find the shear force for this beam. I'm quickly going to wipe this off. Now this beam contains a UDL throughout its length. So in looking for the shear force, we're going to determine A right, A left, B left, B right, C left, C right. So we're starting with point A. As you can see, there's nothing at A left. So we have it as 0 kilonewton. A right is equal to the shear force at A, which is equal to RA, which is equal to 2 kilonewton. Next is B left. Now this involves the shear force from A to the point at B, but it does not involve RB. This shows that it's at the left-hand side of B. Now the distance for the UDL from A to B is 4 meters. That is why we're converting it with 4. Now we have 2 minus 2 times 4, which is 8. And we have the shear force at B left to be minus 6 kilonewton. Next is B right. Now this involves the forces from A to B, including RB. We can either use minus 6 kilonewton and then RB, or we can start from the beginning, RA, minus 2 times 4 plus RB. Resolving this, we have minus 6 plus 12. Now you can see that it's the same. So we'll have our shear force at B right to be 6 kilonewton. Next is C left. Now, as we did B left, it involves all the forces down to C, excluding the force at C. So we start from the beginning, RA minus 2 times the total distance, which is from A to C. The next is RB. We have our shear force at C left to be 2 kilonewton. So I'm just quickly going to write down these values. Our C right can be done in a way that it includes all the forces, including the force at C. We just picked the minus 2 times 6 plus 12 from our C left to be minus 2. So we have 2 minus 2 and we have 0 kilonewton as our C right. Next is the bending moment. Bending moment at point A and at C is equal to 0. C is a free end. A is the support. The only bending moment we're looking for is that which is at B. We can do it in two ways, either from the left to right or from the right to left. Don't worry, I'll do both, starting from the left-hand side. To get the bending moment at B, we have RA times this distance, 4 meters, is a clockwise moment. Now the next is the UDL, which is 2 times its distance times its distance divided by 2. So we have our bend moment at B to be minus 8 kilonewton meter. Next, I'm going to take it from the right hand side. Now pay a little bit of attention because at this point, sign convention plays. So we have the 2 kilonewton force it is supposed to be a clockwise moment, but because we're starting from the right hand side, it will be a negative moment. The UDL also only acts at a span of 2 meters. That is why we're using 2 meters times the 2 meters divided by 2. Resolving this whole equation would arrive at the same answer, minus 8 kilonewton meter. So it's your choice. You can do both. You can pick your preference. All will result in the same answer. Next is to look for the maximum bending moment. Now, maximum bending moment, like I've always said, it occurs at the point where shear force is equal to 0. Looking from our values, shear force changes its sign at point A to B. What this simply means is that from the point A to B, we're going to take a section. Drawing the diagram for this section, we have our UDL, 2 kilonewton per meter. Since we do not know at what distance we cut the section, we'll name our distance x. Now we're first going to bring out the shear force equation in order to get the value of x, and then we'll solve for the maximum bending moment. So we have 3 forces, RA, our UDL, and F, which is the shear force. So we have RA minus 2 times x, converting the UDL to point load is going to multiply its distance, minus F equal to 0. We're going to make F the subject of formula. For maximum bending moment, F is 0. So we're going to substitute F for 0. When F is equal to 0, so we have our distance as 1 meter. This means that the bending moment occurs at 1 meter from the point A. Now that we've gotten our value for x, we can proceed to providing an equation for bending moment and then substituting x into it to get our maximum bending moment. Just going to write down the values so we do not forget. Moment at B is equal to minus 8 kilonewton meter. For the maximum bending moment, we have RA times its distance x. The next force is the UDL. It's an anticlockwise moment, multiplied by its distance, multiplied by the distance divided by 2, because it's going to act at the middle, dividing it into x divided by 2 and x over 2. The next is the moment, which is acting anticlockwise. Now make moment the subject of equation. We have RAX minus 2 times x over 2. So this is our equation for the bending moment. Now we substitute the value of x, which is equal to 1. So our moment, our maximum bending moment, is equal to 1 kilonewton meter. Now you would realize that we have both a positive and a negative moment. Now you'd know that the moment moves from positive to negative. Another point where moment is equal to 0 is called the point of contraflexure. So we're going to solve for the point of contraflexure simply by using the equation we got for maximum bending moment. Now at this point, we are looking for the distance at which moment tends to 0. So we substitute m is equal to 0 and then look for the value of x. Factorize 2x minus x squared. We have 0 equal to x is common, so we have x, 2 minus x. Now divide both sides by x. Collecting like terms, we have that x is equal to 2 meters. So this simply means that the point of contraflexure occurred at 2 meters from point A. The next thing to do is to draw the shear force diagram and the bending moment diagram for this equation. POC simply means point of contraflexure. Now for the shear force diagram, we start with A right, which is 2 kilonewton, A left is 0 kilonewton. So we barely do not need to consider it. I'm just going to mark out the point here, which represents 2 kilonewton. For B left, we have minus 6 kilonewton, which is a negative force. It's going to be at the bottom. B right, we have 6 kilonewton. C left, we have 2 kilonewton. It's going to be on the same line as A, as it is the same value. And then C right, we have 0 kilonewton. Mostly 2 or not necessary. So we have a UDL. So we join these points by an inclined line. Accordingly, A to B left, then to B right, and then to C left, and then back to C right, which is 0. And this is what the shear force diagram for this beam looks like. At the point where shear force crosses to the negative is 1 meter. That is where maximum bending moment occurs. Next is to draw our bending moment diagram. Let's label the point where maximum bending moment occurred D. The first point is at A, which is 0, and at C, which is 0. The bending moment for B is minus 8 kilonewton meter. We're also going to note the point of contraflexure and also the maximum bending moment. Now we're going to draw down the maximum bending moment line. So here we're going to mark out the maximum bending moment, which is 1 kilonewton meter. Next is to mark out the point of contraflexure, which occurs at the middle of A to B, which is 2 meters from point A. So let's say it's somewhere here. We're also going to draw it down to meet the bending moment diagram line. Now that we've gotten all our points set, we're going to have to join these points with a curve as we have a UDL throughout its span. and then to the final point, C. This is a bend moment diagram for this equation.